Wow, so what data? God. Now Colin loves data. I'm not such a big fan myself, but Colin loves data, so we're going to get him to show us how well the computer can actually deal with this stuff. As you'll see, 3 sections. We'll just have a quick look at each section to see what we get. We're going to get the computer to actually plot it as a curve, and from that value on that curve, the computer can obviously take out quite accurately what is the distance between maximum and minimum peak. It will take that and divide it by 2. So our target, 1.00, is what we're aiming for. Colin, would you like to just start us off with that first section there?
Right, if we zoom in on a small section of data that seems to be reasonably reliable, we've got something that is a bit, there are some unexpected oscillations here, but it's not far off something that you could just about convince yourself was a sine wave. The data here, the package here allows you to try and fit a curve of best fit, and taking into account the variation in there, we've got a set of parameters that are causing this black line. I'm not sure whether that's clear on the video there, but it's giving an amplitude of plus and minus 0.87.
Okay, so about 13% away from what we'll be looking for there. Can we take it back and try perhaps one of the other sets of data and just see, because the middle one, where it's going slightly faster, it did seem to be running more smoothly. I wonder if that's had an effect on this one.
Okay, again let's zoom in on a region that looks reasonably steady there. Again, similar shape pattern there. Try and fit a curve to that region of data. And looking at that, slightly better at giving an amplitude. The amplitude value in this function here is the value A, which is reading 0.94, plus or minus 0.94.
So about 6% error, it's still slightly low. You may be able to see the points are more sort of filling the curve as well. It seems like a happier set of data. There is one further set we had, although it curved upwards, we could sample a small part of that. So that end might be worth a look as well.
I just choose a region that appears to not be increasing all that much. It'll be a small amount of data that I'll use here. Again, a sine function. And that there, again, fits most of the data reasonably well. 0.98.
Oh, 0.98, this is getting good. Now, as you may have noticed, each one of those seemed to get better, seemed to get closer to the answer. We noticed that, and to be honest, it does seem that at slower speeds of rotation, particularly given the device we're using, a drill chuck, actual play in the chuck seems to be more significant. Logically then, let's improve the experiment. Having noticed that, let's go back and try perhaps even a slightly faster one to just get a final sort of idea on how this goes. A bit more dangerous, I'm afraid. Do you fancy the challenge?
Yes.
Oh, I was hoping I wasn't going to say no. I didn't know what to do with it. Right. Just get set up. Okay. I'll get it spinning first, shall we?
Yeah.
Righty-ho.
Okay.
Spin steady. Yep.
Good.
Nobody heard.
Again, reasonably steady, but actually the first thing that we notice straight away just with this analysis here, it should vary by plus or minus 1 Newton, and from that complete set of data, just from 10 seconds, you can see that it's clearly varying from almost exactly 26 up to 28. But let's have a look, see what the computer can do in terms of doing a line of best fit on a small region of that data. Most of that looks reasonable. I choose that and set the function, try and fit, slightly adjust it because I'm better than the computer, and now what I did there is that I set the data and it was fairly close to 1, it was actually 0.98. I've artificially set the amplitude to be plus or minus 1, but if you look at the data here, again, paying particular attention to the peaks, you can see there's a number of peaks where the data doesn't reach it, but equally there's probably a reasonably similar number of peaks that are overshooting it, so a value of 1 seems to fit that set of data reasonably well.
I'm convinced. I don't know about you, but I'm convinced. Wow. I mean, it's just worth it. I know we've used the data a lot. Just worth seeing how powerful this is. From this also, you can get a very accurate reading of how fast this is spinning. More details you'll see later on, but that's going at 34 radians per second at the moment, or just over 6 revolutions per second, 360 RPM. Wow. An engine, I just point out, spins at somewhere near 1,000 even when it's not accelerating. If I put my foot down in my car and my car engine accelerates, it will go up, sometimes to even 10 times that speed. All the parts zooming that fast. All these changes in forces, and yet they last for years. Quite remarkable, I'd have to put it, how well this works. Anyway, yet again, Colin, I'd have to say thank you for your assistance on this. God, don't you just love physics?